All right. Happy Tuesday. We're Tuesday, week 5. So this has been the test looked really great. Generally, so the mean was about where the normal average is. It was pretty much right where the average usually is. The median was great. The median was slightly higher. So it was pretty good. The median is usually right around 80, and I think our median was 84, so that was pretty good. Do you guys calculate your Z-scores at all? See where you stood compared to everybody else? If you don't know, it's in discussion is in week 5, and I posted in the week 5 discussion the test score numbers. So you don't have to tell me what your Z-scores are when you calculate them, but it's kind of fun to kind of see where you are compared to the rest of the class by using the Z-scores. It's kind of fun. It's just a fun little thing since you now have the knowledge to do that. So we're jumping into chapter 6, and thankfully, we're doing one section today and one section on Thursday. So it's not going to be as long as when we did 3 sections last Thursday. So we are going to oh, wait, before I get going, there is a Tuesday coming up. I think it's a Tuesday, might be a Thursday coming up where we have scholarship night at the high school. As soon as I have that date, I'll let you guys know because I'm going to need to not have class that night and either double up on the Thursday or have you watch a video. We'll discuss it and I'll let you guys decide what to do. And because I definitely need to be at scholarship night for the high schoolers, I'm presenting some scholarships. So I'm going to need to do that, but that's in the future, and I'll let you know when I have that date, and we'll plan accordingly. So, first thing we're going to do is we're going to talk about discrete and continuous random variables. You already know what discrete and continuous are. This isn't really new, but it's leading us into what we're doing next. We're going to look at probability distributions with discrete variables. We looked at some continuous ones previously. It's basically the same thing. And then we are also going to look at the mean of discrete random variables. And this is calculated a little bit differently. And I'll show you how to do it with the calculator also. And we're going to interpret that mean as something called expected value. Then we will also compute the standard deviation of the discrete random variable. And we're mostly going to do that in the calculator. There's a way to hand calculate it, but we've already learned that hand calculating standard deviation isn't fun. So we're going to rely on our calculator mostly. I'll show you how to do it by hand, but we're really going to rely mostly on our calculator. I think the PowerPoint that you downloaded will have a spot to where you'd hand calculate it, but I deleted that off of mine. So we are going to stick with our calculator. Calculator's your best friend. So that's where we are today. And I'm sure you saw in the email that I canceled lab 4. We're not doing lab 4. We will do lab 5 in a few weeks, but right now we're just not doing lab 4. All right. So a random variable is it's just a variable. So the variable it's the numerical measure of the outcome from a probability experiment. So for example, rolling dice, the random variable would be whatever comes out on the dice, whatever outcome it is. I think we're going to be using renting movies from Netflix, probably watching movies on Netflix and shooting free throws. So if I have the possibility of shooting three free throws, if I shoot 3 of them, getting 1 in, getting 2 in, and getting 3 in, those would be my random variable. Now we usually use a capital X to denote our random variable. Think it's kind of funny that in stats, the variables that we use, both the capital and the lowercase, they are really hard to distinguish between them. And I'm not going to get mad at you if I can't tell if you used a capital or a lowercase. It really doesn't matter all that much. So capital X, lowercase x, I don't really care. And I think that I pretty much use them interchangeably, but we usually use a capital X for a random variable. And there's no good reason why. This is just what we do. So we've already kind of done discrete and continuous, and this is really no different. Discrete random variable, there's a finite or a countable number of values. If I was going to graph them, I would lift my pencil between them. So for example, shooting free throws. I can't shoot 1.5 free throws. I shoot 1 free throw, 2 free throws, 3 free throws. I can't shoot a partial free throw. So that would be discrete. Continuous has infinitely many values. So we're talking about things that can take on any value. If I plotted it, I would not lift my pencil when I graph it. So, taking a moment throughout the day and looking at the temperature. Temperature is always continuous. Time is continuous. Weight, measurements like that, those are generally continuous. We are going to be focusing in this chapter on discrete variables. So, or at least today. So we're going to, continuous is a thing, but we're just going to put that in our back pocket and focus on discrete today. All right. So distinguishing whether they are discrete or continuous. I'm hoping that by now we've got these down. So the number of light bulbs that burn out in a room of 10 light bulbs. So I can't have a partial light bulb burnout. So this would be discrete. The number of leaves on a randomly selected oak tree. Though a randomly selected oak tree will have thousands and thousands of leaves, you still could technically count them. So this would also be discrete. The length of time between 911 calls, it can take on any value. There could be 5 minutes, 38 seconds between 911 calls, and I'd have to be waiting 5 minutes before I could wait 5 minutes and 5 seconds. It can take on any value, so this is continuous. Questions, or are we feeling okay with discrete and continuous? All right, we will move on then. So we already also talked about a probability distribution. So a probability distribution, it probability distribution, the probabilities will always add up to 1, and all probabilities are between 0 and 1 inclusive. So it could be 0, it could be 1, or it could be anything in between. So a probability distribution for a random variable, we have to have all of the possible outcomes and then those probabilities of those outcomes in your graph. And you could put it in a table or a graph or a mathematical formula. Generally, we look at it at the table and call that our probability distribution, but it can take on any of those values, or it can be in any of those ways. I can call a graph a probability distribution, but sometimes it's harder to read unless it's a pie graph. But probability distribution is just the table. We've already kind of looked at these, and they're between 0 and 1, and they add up to 100%. So hit this one right here. This is a probability distribution. So all of my percents, if I added them up, they would add up to I would add up to 100%. This shows the number of movies streamed each month with Netflix. So I guess they asked a bunch of people how many movies they stream each month Netflix, and people gave their answers. And apparently nobody gave an answer higher than 5 because my probability distribution has to contain all of the answers. And then we have our probabilities right there. So this right here is a probability distribution. I love that we're starting with kind of review stuff before we get to the meat. The real meat is on Thursday, but we've got this one, it gets a little bit meaty today. Just a little bit meaty. Okay. As I already kind of told you this, we talked about this before. Our rules for a probability distribution. This right here is a summation. I think I've already told you that before. That just means add them all up. Add up all the probabilities and they will equal 1. And then number 2 is they're between 0 and 1 inclusive, which means they include the 0 and 1. I can have 100% or I could have 0%, but they will be between 0 and 1 inclusive. I believe the next test will have questions on it that will ask you whether or not things are a probability distribution. So they need to have those two things. They all need to add up to 1, and the numbers need to be between 0 and 1. I can't have a negative probability, and I can't have a probability that is 12. So they need to be between 0 and 1. So a probability histogram, um, it's same thing as it's exactly the same thing as the relative frequency histogram. It is exactly the same thing. We like to just rename things. I don't know why. But your probabilities would be on your vertical axis and your random variable outputs would be on the horizontal axis. It's exactly, it is a relative frequency histogram. The only thing is your vertical, you would just say probability instead of relative frequency. Otherwise, it's exactly the same thing. No difference there. I know I've gone through, like whipped through 8 slides without any real new stuff, but so far are we good? Any questions so far? Okay. All right. So this is a probability histogram for the movie streamed on Netflix. So notice it says probability on the vertical. It's the number of movies streamed because this is um, discrete. We just put the values smack dab in the middle instead of putting them on either edge. Discrete, you just put it in the middle of the bar. And so this is just my distribution. You may be asked to read one, but I'm not going to ask you to create one. Okay. All right. There's another way that you can graph this. I hate that they call it a histogram, but there's another way that they can graph it. And basically, it's kind of a shortcut graph. So you can just quickly get a picture. Maybe you're looking to see if data is skewed or something like that. So this one right here is just a really quick like snapshot. It's just the line with a dot on the top. And it's more just to get a picture of the data. So here you can see that it is left skewed because I have the tail on the left. So this is just a way to get a really quick picture without making all your, because it's time consuming to make all of the bars. And so instead of making all the bars, this is just a really quick snapshot. And I don't even know why it was included, but it is part of it all. And there you go. We're going to get into math. I think the next screen, maybe the one after, we're going to actually do some math. So I know you're all just itching to do some math or not. All right. Yes, now we're going to do some math. Kind of wish it wouldn't have, um, I think I'm missing a screen. I swear I'm missing a screen with, oh, there it is. Is that it right there? Feel like I'm missing a screen with the formula on it. Hold on. Maybe not. Yeah, I feel like I am. Okay. The way that we find the mean of a discrete random variable, I'm just gonna explain it because I feel like I'm missing a screen. This is my formula right here. So what you're going to do is you're going to take each of the data values, so each of the possible outcomes. Take each of the possible outcomes, you're going to multiply it by the probability of it happening. So I have probability of it happening right there. Multiply each one by the probability of it happening and then add it together. So here I have the first one. This is my first data value. Yes, 0 times 0.6 is 0. I include the 0 answer just for consistency. Clearly, nobody needs to put this in their calculator and it's not going to change the value at all. But it is just what we do. So this is the first x value times the probability of the first x value. I don't need that parenthesis. Time the probability of the first x value. Then I have the second x value times the probability of the second x value plus the third x value times the probability of the third x value, and on and on and on. We add all of those together, and that's going to give us the average. So the average number of people, this I don't know why it changed it to DVD. I keep meaning to change it to Netflix, and then I just don't. I don't know why they changed the name of it. But anyway, so the average number of movies streamed by somebody from Netflix would be 1.49. Obviously, people aren't watching 1.5 movies. I mean, I guess they could. But when you average things out, we frequently end up with an answer that's not like one of the outcomes. It's not necessarily reasonable, but it is what it is. So the average number of movies somebody would stream from Netflix, I don't know why I'm having such a hard time speaking tonight, is 1.5 approximately, or 1.49. So if I took what this is telling me is that As I get my sample bigger and bigger and bigger, um, I back up a second here. 1 second. So we're going to talk about expected value. I forgot those words. I'm so sorry. I don't know where my brain is today. Expected value is on the next screen. The way that we interpret the mean of a discrete random variable is that if I took a large number of samples, if I continued getting more and more and more and more samples, I would expect the average of all of those samples to get closer and closer and closer to the real average. So take a look here. So if I have a small sample here and I got an average of less than one, and then as I'm getting more and more samples, I am taking the average with more and more and more samples. I would expect the average to approach whatever that true average is. This is called the law of large numbers. If I keep taking more and more samples, we call this the expected value. Because I would expect, as I have more and more samples, I would expect that my average would get closer and closer and closer to that value. It's kind of like if you're going to a casino, the house knows that you guys know the house wins, right? Most of the time, the house wins. So what they do is they have done the math so that they know that they're going to pay out of just a little bit less than they're going to bring in. So the more and more people that they get to come to the casino, they're going to expect to earn a certain money amount of money from all those people. They know that some people are obviously going to win. They're going to walk out making money. But as they get more and more people, the law of large numbers tells us that the house is going to win, that in the end, the house is going to make money. So it might be for that it averages out that every dollar people pay in, the casino is going to earn 2 cents on every dollar or 5 cents on every dollar. So if you pay in a dollar, the casino is going to be making $1.03. They're going to make a little bit more money, or you're going to lose 97 cents of every dollar because they're going to make a little bit more money than you're going to pay in. Law of large numbers tells us that in the end, the casino is going to win. This is the kind of math that they use. And I think as I go on, this is going to make more sense. All right. So this is kind of what I just said that because the mean of the random variable represents what we expect to happen, we call it the expected value. I would expect if we kept repeating the trial over and over and over again, that's what I would expect the average to be. We write it like this, E of capital X. We frequently write it like that. It's expected value of X. So you might see that on your homework. It might ask you to find E of X, and that's what it means. Find the mean of that discrete random variable. I've got a couple examples. We will do this. And I'm going to show you how to do it in your calculator. All right. So, term life insurance policy will pay a beneficiary a certain sum of money upon the death of the policyholder. These policies have premiums that have to be paid. So, life insurance company sells a $250,000 one-year term life insurance policy to a 49-year-old female for $530. So, I'm going to put that right here. If she survives the year, the insurance company makes $530 off of her policy because they are not paying it out. And the probability of her surviving is 0.99791. That's the probability that one 49-year-old female will survive. Now, it is possible that she passes away. If she passes away, they are paying out $250,000. So, but technically, they've only lost 249,470 because she paid that $530 for the year. But the probability of her dying is the complement of the probability of her living. So 1 minus 0.99791. So the probability that they have to pay that out is that right there. So obviously, at least there's going to be some woman that dies, some 49-year-old woman, they are going to be paying out that money. But what they're counting on is them selling a whole lot of these policies. If they sell a whole lot of these policies for $530, they're going to expect to make money. So here's the math right here. So our expected value of each policy, take the $530 that you pay out times the probability of her surviving. Then you take, or that the 530 is what she paid out, the 249,470 that they lose if she passes away, times the probability of her passing away. We're going to add those two values together. So based on this, the expected value of each of those policies is $7.50. So they're expecting each of these policies to earn them $7.50 based on the probability that somebody dies and somebody lives. This is what actuaries do. Actuaries sit in a room and they calculate these probabilities so that insurance companies are making some money on the policy, but they're not making so much money that it's not even worth it to buy it. So they want to make sure that it's profitable for them, but also isn't too expensive. And there's some optimization things and all that that they do. So this is a little bit simplified, but because so each policy in the long run is expected to be worth $7.50. Any questions here? I've got more examples. All right. We're going to talk about free throws. Nope, we already did this one. I thought I had the free throw one. I do, it's right there. Okay. I'm going to talk about standard deviation and then we'll do mean and standard deviation of the next one. So standard deviation has the same basic meaning here. It has the same meaning, but we have to calculate it a little bit different. So you calculate your expected value. That's what this is right here. We call it mu sub x. So our expected value, that's the symbol we use, mu sub x. Standard deviation for these discrete random variables is sigma sub x. So you take the outcome of your variable, subtract it from the mean, or subtract the mean from it, sorry, and then square that value. Then you multiply that by the probability of it happening, and you take the square root. We're not doing any division here. And that's the standard deviation of your discrete random variable. We are going to do one calculation by hand. Then I'm going to show you how to use your calculator for all of this. You won't even have to do the mean by hand or anything. You'll put it in your calculator and it'll be great for you. So here we go. So we're going to compute the mean and the standard deviation of these free throws. So somebody throws, these basketball players shoot free throws. These are the probabilities of each of these. They try to shoot three. This is the probability of each of these outcomes. So first, we're going to calculate our mean. So it's mu sub x. So 0 times 0.01 plus 1 times 0.1 is 2 times 0.38 plus 3, 0.51. And I'm going to put this in my calculator. Okay, so I got my mean, 2.39. Please let me, oh, good. Thank you, Gwen. Good job. I was just going to say, let me know if I calculated incorrectly. Clearly, I did not. So, all right. So now we're going to do the standard deviation. So sigma sub x. So I'm going to take, so this one is just 0, but still I'm going to do 0 minus our mean, which is 2.39 squared times the probability of that outcome. I'm going to add it to the next one. So I have 1 minus 2.39 squared times the probability of that outcome plus 2 minus 2.39 squared times the probability of that outcome, and I ran out of room, plus 3 minus 2.39 squared times the probability of that outcome. This is really ugly. Let me do this again. You can put all of this in your calculator at once if you're really use parentheses just as I have them written. That's my phone. That's not the calculator. So let's do this. So if you use parentheses exactly how I have it written, you should be fine. And if you don't typo like I just did, you'll be even better. This is still easier than the other standard deviation. So here I got 0.4979. See if anybody else is calculating and see if I got it right. Because I don't always trust myself. Okay, thank you. Good. Thank you, Gwen. So now our final answer is going to be the square root of that number. Whoa, I didn't want to do that. I usually just leave the number in my calculator that I already have, take the square root. So our standard deviation then, 0.7056. I probably could just stuck with 0.7. So the standard deviation here is 0.7. So this kind of gives me an idea. So obviously, two standard deviations above that doesn't really make sense, but it is what it is. It is what it is. Because we're left skewed, mean and standard deviation are kind of weird here, but we generally don't use median for these discrete random variable probability distributions. You guys want to learn how to do this in the calculator so you don't have to do it by hand? We've already kind of sort of done this. Let me show you. I'm going to pop over. Unless questions before we do that? All right, I'm going to pop over to my calculator. Popping over. Okay, so go into your lists. So stat, edit, and I'm going to need list 1 and list 2. So I'm going to clear those out. In L1, you're going to put in the outcomes for your discrete random variables. And in list 2, you're going to put the probabilities. And then you're going to look back and make sure you didn't typo, because that's my most common error. I'll give you a moment, make sure you have those in there. So you put the outcomes for your discrete random variables in your list 1, then the probabilities in list 2. Anyone need another moment? All right. So now we're going to go to one variable statistics. We've been here before. So stat, arrow over to calc, and we want one var stats. Mine's already here, but if it's not already there for you, your list, your X value is in L1. Your list is there. Your frequency list, L2. Because we want it to take that first number and multiply it by the second number. It knows what it's doing. We just trust it. So your list would be an L1, frequency list is L2. And then you're going to go calculate.
How do I change my frequency list? Or how would I
Okay. So to get the L2 there, you just do second 2 to get L2 there.
let's see. Okay, got it.
Perfect. and then just go down to calculate. So this is what we got. We got 2.39. It's awesome. And it only gives you it only gives you the population standard deviation because there is no sample standard deviation for this particular thing. And this is exactly what we calculated. So this is beautiful. And this right here, this right here is just sum of all of them squared. I don't know why we need that. It gives us mean, median, and all of that, but we don't really use those. Or, I mean, it gives us the median and the quartiles and all that, but we don't use those. All you need is this X bar, which is your expected value, and the standard deviation. And that's all I expect you to find with these. So what it's saying with the 2.39, our interpretation here is that if we were to have these basketball players shoot like a whole bunch of sets, many, many, many sets of 3 free throws, we would expect, pop back over here, we would expect that their average would be 2.39 out of the 3 free throws they would make. This is the average over a very large amount of number. That's what we would expect that average to be if we kept having them go up and shoot three free, that's so hard to say, 3 free throws, like different sets over and over and over again. If we kept running these trials, we would expect the average number that they would make would be 2.39. It's the law of large numbers. That's our expected value. Questions? I think that was it. Yeah, this is a really short class. I think I mentioned that to you on Thursday last week that you guys were going to be get a short class today. Thursdays is going to be a little bit longer, but today is pretty short. They're not evenly weighted, 6.1 and 6.2. They're not evenly weighted, but it wouldn't make sense for me to jump into the next one. So what I want from you, any questions while we are on recording? I'm happy to jump back to homework questions or anything else for the good of the group that needs to be on recording.
I had a little hand in homework question
Okay.
on the
Is it
last page.
is it for the six, the we or what is it?
That's the one that's due today.
The one that's due today. Where is it?
Yeah.
Okay. Is it this right here?
Um,
Okay. The week 4.
let's see. Let's see.
I see. I will open it up. Let me see here. Maybe
Oh, yes, week
this one.
4. Yeah, you're
Okay.
right.
What do you
Cool.
got?
Um, question 3.
Okay.
Um, so if it's let's see. So the number A, or yeah.
So this
So if it's an and male, and you just add to addition. No, it's a
right.
multiplication.
And is
Multiplication.
multiplication.
So and then on C, where it says, so the Gallup pulled out on C says 10.6, but it's not the number that I got for A.
And you shouldn't have, because in letter A, you are assuming that betting is independent of gender. So what it means on letter A is that, overall that a person basically they're trying to say that men don't bet more than women or women don't bet more than men. So what they're saying that they're saying up here that betting and gender are independent. But because this number is different than this number, it's saying that that assumption up here is probably wrong. Because this number is higher, and this one was that they're male and bet on sports, it's actually higher than what we got up here. Then
Right.
probably more men tend to bet than women. So betting is probably not independent of gender. That's basically what's going on with C, is you're just saying that that assumption is probably wrong.
So basically, if I use, yeah, the assumption, then I'm just multiplying the two statistics, but in reality, the statistics that I'd be using would be different.
Right. So we can
So,
only use the and probability rule of multiplying them together
mm,
if the two things are independent. But these ones, this is showing because this number is different, it's showing me that in A, this is probably not correct. I mean, it's correct for this problem, but in general, it's probably not correct because being male and bedding are not independent, or gender and bedding are not independent. So all you're saying here is that the assumption that bedding is independent of gender is probably wrong. That's all you're saying in letter C.
because those two at the top under three, those are independent numbers. Essentially, like 17% of adult Americans, they're not indicating whether it's male or female,
Right.
but they're giving you just 17%.
Right.
And then assuming like, well, the other number is correct, but
Yeah.
okay,
Because
not
we're
explain that, but
assuming that they're independent, we are
right.
there shouldn't be like overlap. That it's just it would be any random person, but technically males are probably more likely to bet. So this one right here is assuming independence. Down here is saying, okay, these are not independent. This is the real number. So then with D, you're going to recalculate what you did at B with B. You're going to recalculate it using this number instead.
Right.
Instead of
And
the
B,
number you got in A, you're going to recalculate it using this one.
okay.
Does that make
And then
sense?
yeah. Yeah, okay. And then B, I I did the addition of the 48%, the 17%, and then
What you got for A.
minus what I got for A,
Right.
right? Okay.
Yes, but you're
All
going to
right.
replace that with this when you're doing D.
Okay. All right, let's make it sense then.
Okay, good.
Seemed too simple.
And
So,
sometimes it does, and sometimes you just overthink it. I mean, I do that all the time where I overcomplicate everything. It's just in my nature. So good. I'm glad
all right, yeah.
that you were able to get that figured out. Any other questions on the hand and homework since I have it up here? Anyone else? All righty. I'm going to get off of that. And any other questions while we are recording before I stop the recording? Okay, I'm going to stop the recording then.